and that's to do with the autonomic nervous system. I mentioned it casually in passing, but let's try and bring these pieces together and talk a little bit more about the autonomic supply to the heart and blood vessels. People sometimes worry when we talk about the central nervous system and they're, oh no idea what you're talking about. But I hope you'll see that it's actually quite simple. It's quite simple. So, what do we see in this diagram? We can see the sympathetic and parasympathetic system in the context of blood vessels and the heart. Not other systems, not the gut, not the kidney. No, we're just talking heart here and blood vessels. And if we look at the parasympathetic side of things, that red dashed line, you can see that it's quite limited, isn't it? Not much going on. So you can see that there's a parasympathetic innervation from the brain, from the vasomotor center. But from the brain, you can see that it heads off to the heart. Can you see that? And we know where it goes. It goes to the machinery that controls the rate. It goes to the sinoatrial node, it goes to the AV node. Okay, that's the red dashed line, mainly. If we look at the sympathetic, here we are, the sympathetic chain. Can you see these two chains here, these chains? So it comes from the brain, and then through these chains, and these chains send out fibers. Call them efferents, if you like, or motor fibers, doesn't matter. These fibers, as you can see, feed not only the heart, but also blood vessels. So what that tells us is that the parasympathetic affects the heart, yes, affects the heart rate, but the sympathetic affects the heart and the blood vessels. Yeah, it has innervation. Parasympathetic doesn't, though, does it? The parasympathetic goes to the heart, sure enough, but it doesn't go to blood vessels. Yeah? Oops. Now, when we get down to the business end of blood vessels, this is what you find. Aorta, smaller arteries, arteries feeding arterioles, arterioles feeding capillaries, yeah? Capillaries uniting to venules, veins collecting together, bigger veins heading back to the heart. This is the system. And what this little diagram shows the innervation. The sympathetic nervous system, what's it innervating? It's innervating all the different parts of the blood vessels except for capillaries. Yeah? So there's sympathetic innervation to the arteries, to the arterioles. Arterioles, remember the arterioles. Remember that diagram I showed you in the first class? Pulsatile blood, getting less and less and less, especially in the arterioles. These arterioles regulate the blood flow through capillary beds. Very important, the arterioles. Major organs, if you like, of blood pressure regulation in capillaries. So, not surprising, is it, that the sympathetics innervate the arterioles? Now, what you might imagine now, how does this system work? Okay, I've got blood vessels all over the place. I've got blood vessels to my gut. I've got blood vessels to my muscles. When I run, I need blood going to the muscles of the legs. I don't need blood going to the kidneys or the GI tract, do I? When I'm eating food, I want blood to be going to the GI tract, but I don't want blood to be going to my muscles. Yeah? Makes sense, doesn't it? We've only got about 5 litres of blood in the body, so we need to distribute that blood efficiently. When we run, we need more blood to the muscles. When we eat, we need more blood to the GI tract. We want to optimize the use of that blood. So you could imagine that these sympathetics, imagine this was sitting in a muscle and now starting to run. You can imagine the sympathetics will cause these to dilate. Yeah? When I'm eating food, imagine this is a vascular bed in the gut. You can imagine that the sympathetics will dilate the blood vessels in the gut. If we were to look at the muscle over here, we'd find that those vessels would be constricted. You see? So it's a question of one size or one chemical can do 2 jobs. Yeah? So with sympathetic innervation, you can either get these to dilate or constrict. Yeah? That's a more efficient system than having to have parasympathetic and sympathetic innervating blood vessels. Because you have to have more wiring, more cables, much more space is needed. But if you can get one division to do both jobs, that's good news, isn't it, for the blood vessels? How can it do that? How can it work like that? Well, it can work like that because at rest, our blood vessels are in a state of tone, if you like. There is some sympathetic stimulation at all times. There's some level of sympathetic stimulation that causes the blood vessel to have a certain size. Now, what that means is that if the sympathetic gets less or more, it can control that size, can't it? Yeah? So if the sympathetic stimulation increases, for instance, it could cause the blood vessel to constrict more. Then it goes back to its normal tone. If the sympathetic stimulation is removed, it can dilate. Yeah? So that's the idea. One size can do, one chemical, if you like, can do both jobs. It can cause dilation or constriction. So the vasomotor center, vasoconstriction, vasodilator areas transmit sympathetic impulses through the cord and the peripheral sympathetic nerves to almost all blood vessels, except, as you can see, capillaries. Continuous partial constriction of blood vessels normally caused by sympathetic vasoconstrictor tone. So what does that mean? It means there's a certain level of sympathetic stimulation at all times, but that can be reduced or increased, so it can cause dilation or constriction of blood vessels. If you look at the overall picture, here we've got the brain, we've got the higher centres of the brain, and we've got the hypothalamus. You may have heard of some of these bits and pieces, doesn't really matter. We've got the medullary centre, okay? And you can see within the medullary centre you've got two parts. You've got the parasympathetic, vagal, and sympathetic. And you can see that from the vagal side, you've got innervation to the heart. And from the sympathetic side, you've got innervation to the heart, and you've got innervation to blood vessels. In general, vagal is inhibitory, hence the negative sign, and sympathetic is excitatory, hence the positive sign. Yeah. We know now vagal stimulation of the heart will reduce the rate. Yeah. We know that sympathetic stimulation of the heart will increase the rate and the force. And we know that the sympathetics can also regulate blood vessel. Because in the blood vessels, of course, you've got smooth muscle, haven't you, around this central part. Smooth muscle, if that smooth muscle is caused to contract or relax, it's going to make the blood vessel smaller or larger, isn't it? Yeah? Little bit more complicated, this sort of also shows feedback mechanisms, because the brain needs to know when to sympathetic or when to parasympathetic. And how does it know? It's based on feedback, it needs information. So what you can see is brain, we've got the sympathetic chain, sympathetic nerves heading off, and you can see that some of those nerves go to blood vessels, other of these sympathetic goes to the sinus node and also to the muscle. Yeah? Beta-1 receptors, notice. And you can see vagal, here's vagal, look, sympathetic coming out from the brain, sympathetic coming out. The vagal, on the other hand, just goes to the conduction machinery of the heart, sinoatrial node. Okay. Feedback, information going back to the brain, comes from places like baroreceptors. Can you see here? Aortic baro. Baro simply means pressure. So there are receptors in the aorta and elsewhere that measure pressure. Just like in your car, you've got devices that measure temperature of the car engine, haven't you? You know when it's hot or when it's cold. Here, you've got pressure receptors inside the aorta, for example. It sends signals to the heart, to the brain, saying the pressure in the aorta is so much. If it falls, or if it rises, sends those signals to the brain, and the brain compensates. So if the blood pressure falls, for example, for any reason, what happens? Sympathetic innervation is increased. Increase the force and rate. Pressure goes back up again. Yeah. Other things that can change in blood are things like pH. So there are chemoreceptors, chemical receptors that send information to the brain. Oops, the pH has changed. Or oops, whatever's changed. Send the signal to the brain sends out parasympathetic or sympathetic innervation and compensates for that. You see the idea? Yeah. Also in this diagram, we've added in that the sympathetic nervous system stimulates the adrenal gland, the adrenal medulla actually, to produce adrenaline. So adrenaline circulates in the blood, but noradrenaline is released from nerve terminals. Can you see that difference? So one you might consider as the transmitter, neurotransmitter, and the other you might consider more of a circulating hormone or circulating chemical. But they both have the same effects. Adrenaline, noradrenaline, epinephrine or norepinephrine. At the end of the day, they can both increase the rate and force of the heart, and they can both influence the state of blood vessels. Okay. But this idea of feedback is important, isn't it? We need to have that feedback. A small video.
In this video, we'll discuss how heart rate is controlled by nervous innervation. So if I could first draw your attention down to the aorta and the aortic arch, you'll see that we have some aortic baroreceptors located on the aortic arch. We also have baroreceptors up here on the internal carotid artery. These are called the carotid baroreceptors. And these carotid baroreceptors are located on a swelling on the internal carotid artery. This is called the carotid sinus. So the carotid sinus is a swelling on the internal carotid artery, and on that swelling are located the carotid baroreceptors. So we have two kinds of baroreceptors. Baroreceptors are stretch receptors that can detect the change in pressure, the change in stretch on the arteries, and then send signals via their nerves that they're connected to up to the medulla oblongata. So we have the aortic baroreceptors, which are sending information about blood pressure up the vagus nerve to the medulla oblongata. And then we have stretch receptors or baroreceptors on the carotid sinus of the internal carotid artery, sending information about blood pressure up by the glossopharyngeal nerve. This is the glossopharyngeal nerve here, into the medulla oblongata. So we have information coming from two sources, from the aortic baroreceptors and the carotid baroreceptors. Now this information about blood pressure, whether it's high or low, is integrated in the cardiac control center within the medulla oblongata. And then a decision is made by the cardiac control center. Is the blood pressure too high? Is it too low? Above the, or around the set point. So remember, in the cardiac control center, there is a homeostatic set point of what blood pressure, a range of what blood pressure should be in. If it goes too high or too low, the cardiac control center has to then send an efferent signal or a correction signal down to the heart to increase or decrease the blood pressure and bring it back under homeostatic control. So, if the blood pressure is too high, a efferent signal can be sent down, back down the vagus nerve. Here you can see the arrow. If the blood pressure is too high, an efferent signal can be sent down the vagus nerve via parasympathetic fibers and innervate the SA node. And what this will do is it will release acetylcholine, and acetylcholine will have an inhibitory effect on the SA node and slow the heart rate down. Okay, so if blood pressure is too high, a correction signal can be sent down the vagus nerve via parasympathetic fibers, which release acetylcholine on the SA node and slow the heart rate down. On the opposite end, if the blood pressure is too low and we need to increase the blood pressure to get back into that homeostatic range, a correction signal is sent via sympathetic fibers down the cardiac nerve, where the cardiac nerve here, there are 3 cardiac nerves which come out of the cervical ganglia, and the cardiac nerve then releases norepinephrine at the SA node and increases the heart rate. So we have, okay, just to summarize, we have 2 inputs, the aortic baroreceptors and the carotid baroreceptors, sending afferent information about blood pressure up to the medulla oblongata and into the cardiac control center. And then depending on whether the blood pressure is too high or too low, a correction signal can be sent down either via the vagus nerve and parasympathetic fibers to inhibit and decrease the heart rate, or via sympathetic fibers via the cardiac nerve to release norepinephrine and stimulate the heart rate.
Okay? So, oops. So just a few points here. All blood vessels except capillaries receive innervation by postganglionic sympathetic nerves that originate from the sympathetic chain. Just like what I was saying before, capillaries are the only parts of the vascular system that don't receive sympathetic innervation. The distribution of adrenoceptors varies from organ to organ. We talked about beta-1 adrenoceptors in the heart already. Adrenoceptors are beta-1, beta-2, alpha, different kinds of receptors.